Julio Martinez from IHES on soft theorems from higher symmetries. So please.
Okay, well, first of all, thanks a lot for the invitation to this very nice workshop. I wish it was in person so I could visit Portugal again, but okay, I guess we'll have to be content with only. So I'm going to tell you about this work that I put out earlier this year with my student Jonah Berian-Dutcher, and also a former student of Cliff Chung at Caltech, which now is a postdoc at Uppsala, Maria Derda. So the title is Soft Theorems from Higher Symmetry. And by the way, just interrupt me at any time if there's any questions. I don't have a ton of slides, so I'm happy to expand on anything. Okay, so the talk is about soft theorems. So soft theorems are just some statements about universality when we take the limit when some momentum in a scattering amplitude becomes small. Okay, so we have a massless particle. We are allowed to take its momentum to zero, so just the frequency of that radiation is very small, and oftentimes the behavior of the amplitude is universal, so it takes this form. So when we take this limit of an amplitude with this extra soft particle, the result is some sort of number of some operator acting on the amplitude without that particle. Okay, so a lower point amplitude. And perhaps the earliest examples of this sort of universality is a so-called soft pion theorem, or Adler's zero. So the statement is that if you have a scattering amplitude of pions, say in the Carroll effective theory, so for massless pions, and then you take the momentum of the pion to zero, then the amplitude must vanish. So I'll review in a second where this comes from. And similarly, there's a soft photon theorem of Lowe, Burnett, and Kroll, then also revisited by Weinberg, that says if I take a soft photon, there's similarly some soft factor multiplying a lower point amplitude without that photon, and this soft factor is a sum over all of the charged particles involved in the scattering process multiplied by their charge. This is the polarization of the photon, and this is the momentum of each one of the hard particles, which are not taken soft. Okay, so these are very old statements. Okay, what am I going to say that is new? So there's many perspectives on why these soft theorems exist. So for instance, there's the symmetry perspective. So there's statements that soft theorems, say for photons and gravitons, have something to do with asymptotic symmetries, with large diffeomorphisms or large gauge transformations. For pions, we typically say that this has to do with spontaneously broken symmetry. If you take soft massless scalars, they might encode the geometry of the moduli space of vacua. If you talk to an EFT person, they just say, okay, these soft theorems are just a statement about factorization between different modes. So soft theorems are just the leading operators in the effective theory for these soft modes. So I always wonder what are the precise connection between this, but I won't attempt to make this connection. But there's something that always bugged me, which is that explaining soft scalar and soft photon theorems required invoking rather different ideas. Okay, so for one of them, we talk about asymptotic symmetries. For the other one, just ordinary symmetries in the bulk of the space-time where the scattering process is happening are sufficient to explain the theorem. Okay. However, in the recent decade, there's been a great expansion in what we understand as symmetry. Okay, so there's a kind of ordinary symmetries that act on local operators, but this has expanded in various directions. So there's these higher form symmetries, which are symmetries that act on extended operators, say Wilson lines or surface operators. There's also higher group symmetries, which are kind of an intertwining between ordinary symmetries and these higher form symmetries, which I'll explain in more detail. And there's even some notion of categorical symmetries or non-invertible symmetries that there's been a lot of excitement about in the literature in the last few years. Okay, so far these ideas have found not much application in scattering amplitudes or in particle physics in general, with a few exceptions. For instance, there are some papers about how to use this to understand the monopole scattering or kind of certain features of particular 2D integrable models that seem to violate crossing, but they don't once you understand the symmetry structure. So today I'm going to argue a new application of this to scattering amplitudes, which is that they can provide a unifying perspective on soft theorems. Okay, so I will use them to kind of unify our understanding of soft photons and soft pion theorems. And also they suggest new structures. So we will see that we will have a new kind of soft theorem that makes photons and pions talk to each other. Okay, so the outline of the talk is first I'm going to review our understanding of soft pions. This won't be new at all. However, I'll present it in a way that will make it completely manifest that the understanding of soft photon theorems is completely analogous. And then I will explain this, the soft photon from some sort of one-form symmetry, and then this new soft theorem associated to a structure called a two-group, which I will introduce, that intertwines photons and pions. Any questions about the introduction? Okay, so let me get started with a review of soft pions. Okay, so pions, what I mean more generally is just kind of Goldstone bosons for some spontaneously broken symmetry. Okay, so a familiar situation is we have some local operator in some quantum field theory, which is charged under some continuous global symmetry. Okay, and this operator picks up a vacuum expectation value, VA, which breaks the symmetry G down to a subgroup G with H, which lives invariant this VEV. Okay, so the typical structure, so here I'm assuming a symmetric coset, is that H is a subgroup. So the generators of H will satisfy usual algebra. There's some generators X that are broken, so these live in a coset G mod H, so they transform us under some representation of H, but they don't close. So if you commute two of X's, you get this. Okay, and there's a Goldstone theorem, which is that this situation implies the existence of an angle boson for each broken generator. Okay, so what is the quick kind of Euclidean proof of this statement? There's a detailed Lorentzian proof, but the quick proof is, let's just look at this word identity. So let's look at the conservation of the current in the presence of this operator that picked up the VEV. Okay, so let's say let's do a U1 example for simplicity. Okay, so this, by the word identity, will have a contact term at the position of this operator, but the expectation value of this operator is a constant. So what we learn is that this correlation function must have some power law decay. Okay, otherwise I cannot satisfy this word identity. And since there's a power law decay, there has to be some gapless mode somewhere in the theory. Okay, and one can see if one goes to the spectral representation of some correlation function that this corresponds to a single particle pole. Okay, so there's this pion field which effectively parameterizes fluctuations of this VEV, which is implied by this word identity and the kind of VEV for the charge operator. Okay, so this is textbook material, nothing new. Okay, so the pions are these Nambu-Goldstone bosons. So more precisely what we have is that there is a kind of an overlap between the current, the spontaneously broken current, and the one particle state, which takes this form. Okay, so this is just a one pion state. I can create it by acting with the current on the vacuum. This implies that the current is linear in the Goldstone. Okay, so this has to have a term that goes like this, otherwise I cannot interpolate this one particle state. And in turn, this implies that the pion will shift, so the symmetry is not linearly realized. Okay, so this term here will tell you that the symmetry is a shift symmetry. Okay, so the paradigmatic example of this is just QCD in the chiral limit, so just the chiral Lagrangian. So we have the chiral symmetry, left and right kind of flavor rotations of the quarks that get broken to the diagonal vector subgroup by this bilinear picking up a VEV. Okay, and there's NF squared minus 1 pions or just Nambu-Goldstone bosons at low energies. And the EFT we can write just in terms of this use, which are the exponentials of this pion field. So they're basically the fluctuations of the VEV, of our order parameter for symmetry breaking. Okay, so how do we show the Adler zero, this soft theorem? It's a very simple current algebra argument. Instead of looking at the one-point function in the presence of a local operator, now let me look at the one-point function in momentum space evaluated in some state alpha, which might correspond to a bunch of particles. Okay, since I told you that this interpolates the pion, there has to be a one particle pole here, which corresponds precisely to, and the residue will be the amplitude with this additional pion. And then there's some remainder. So the word identity, conservation of the current, will imply that these two things need to be related. And then n is smooth as q goes to 0. So if I now take the limit when the momentum goes to 0, then I see precisely that this must vanish. Okay, so this is the kind of three-line proof of this soft theorem for pions. And it's just a current algebra proof. We have a symmetry, we have a current, we apply the word identity, we get the answer. Okay. What about double soft pions? Okay, so we can even derive multi-soft pion theorems, and this relies on the fact that the current algebra also knows about the commutation relations of the broken generator. So if we look at the divergence of a current in the presence of another current, this knows about the structure constants. And a similar argument to the one before, I won't explain in detail, but if you consider the two-point function of the broken current in some state, one can derive a limit when you take 2 pion soft. Oops, and the leading term knows precisely the commutation relations of the broken generator, so it's this F here. And then the subleading term, okay, it's more complicated. It has an angular momentum operator, also the anti-commutator schematically. So, but anyway, so the message is that there's some simple current algebra argument which doesn't rely on any Lagrangian. It's a pure symmetry argument that gives you both single and double soft pion, or more generally, Nambu-Goldstone-Gozon soft theorems. Okay, questions before I shift gears to photons? Okay, so for photons, let me review this notion of a one-form symmetry. Okay, so one-form symmetries, continuous one-form symmetries. Now, instead of having one index current, we just have a conserved current, which is a rank 2 tensor, which is antisymmetric. Okay, because of that, they're supported on codimension 2 surfaces. Okay, so I need to integrate these over a codimension 2 surface. And the charge operators then are not local operators, but line operators. So I need to wrap this surface around the line. And then when I pull it through, then I pick up a phase, which is the integral of the parameter that parameterizes this the transformation, and then the charge of this operator. Okay, and because these are supported on codimension 2 surfaces, these are necessarily abelian. So if I have all 2 of these codimension 2 surfaces, these are conserved charges. So these operators are topological. They only depend on kind of the homology class of this surface. So I can just smoothly deform this configuration into this. So the order of them doesn't have any meaning. Okay, so these are necessarily abelian. And just like in the pion case, the one-form symmetry implies some operator equation. So now, if we have a charge operator, so this will be a line operator, for instance, a Wilson line with charge Q, supported on some curve, then if I evaluate the conservation of the current in the presence of this Wilson line, there is a contact term, and this delta function is just a delta function transverse to the line. Okay, so this tells me that if I integrate this against some surface that intersects the line, I will pick up a non-zero contribution. Okay, so this is the exact analog to this contact term in the case of a zero-form symmetry. Okay, so if you want a more precise definition of this codimension 1 delta function, is defined like this. So you just pick some parameterization of the line with some affine parameter s. This is the velocity, the local for velocity, and then this is a delta function. So this is some covariant version of this delta function. Okay, so for instance, if you fix this s to be the time direction and the line is along the time direction, this delta function is just in the transverse directions. Okay. So now, when this one-form symmetry is broken, spontaneously broken, then some line operator might get a VEV. Okay, so typically we call this perimeter law, but of course this operator is ambiguous up to the addition of a counter term on the line, right? So this we can redefine just to be a constant. Okay, so the perimeter law is just the Wilson line picking up a VEV. Okay, and this is the usual kind of criteria for deconfinement. But from this modern perspective is the breaking of this one-form symmetry. Okay, and the same argument for Goldstone's theorem that I gave before holds here. Okay, so if I look at this correlation function, because this Wilson line has gotten a VEV, there's going to be a contact term, which means that this current now will have some power law decay in the presence of this line. Okay, and that is only possible if there is some gapless mode, which in this case will be a photon field. Okay, so the photon parameterizes fluctuations of the VEV. This is exactly analogous to this equation that I wrote here. And indeed, that's what we do when we write a Wilson line as the exponential of some gauge field. Okay, so as you see, everything is completely analogous. So let's keep going. Okay, so just like for the pion, if we now look at the one-point function of this current in the presence of a one photon state, then this is non-zero. And basically we learn that, that this current is the field strength of the photon plus possibly corrections if the theory is nonlinear. And that means that it's a shift symmetry on the photon, okay, where this is a constant, which in this case is just a closed one form. Okay, so this is all perfectly analogous to the case of the pions. And for instance, in free Maxwell theory, we have also, this is the kind of classic example of this one-form symmetry breaking, where we have an electric one-form symmetry that acts on Wilson lines, a magnetic one that acts on Toff lines. This breaks to nothing, and we have two currents, which are just the field strengths, which are linear in the photon and the dual photon. Okay. So from this perspective, the photon is massless because it's a Goldstone boson, not because of gauge symmetry, nothing like that. It's just, it's a regular Goldstone boson, and hence it's massless. It's some gapless mode that guarantees that this equation makes sense. Okay. However, there's an issue, because now we want to understand the soft photon theorem using this language. However, once we add the charged matter, these one-form symmetries break. But for instance, I told you that the electric one-form symmetry of Maxwell is just the field strength, the current. If I now have charged matter, this is not conserved. There's the electromagnetic current that appears on the right-hand side, which is not zero. Okay, and this is related to two facts. The first one is that Wilson lines can be screened. So I can have pair production that just screen the charge of a Wilson line at infinity. So I try to measure the flux, so that this integral of f at infinity, I might get zero because I have some cloud of kind of polarized vacuum that screens the charge. And also relatedly, the Wilson line can end now in some charge operator, okay, and on the opposite. So they can break. Okay. So this means that a priori, it looks like it's a bit hard to interpret the soft photon theorem in terms of a one-form symmetry. However, note that a one-form symmetry is robust, because since the charge operators are line operators, not local operators, there is no way to add some charge operator to the Lagrangian, which means that even if it's broken, the photon remains massless. Okay. And the magnetic symmetry is still unbroken because it just follows from the water density. Okay. So let's try to see if we can kind of figure our way out of this issue and really understand the soft photon theorem in this language. Okay. So first, let's look at what happens when we integrate out the charged matter. So imagine we have some charged particle, and then we integrate it out. Okay, so for energies below the mass of this charged particle, then we will get something like the Euler-Heisenberg Lagrangian, so some theory of nonlinear electrodynamics. And here, the one-form symmetry emerges exactly. Okay, so this is an emergent symmetry in this theory. The current will be what we said, plus some nonlinear corrections that depends on this Wilson coefficient. Okay, and it's only broken non-perturbatively. So basically only by creation of charged particles, which are non-perturbative in 1 over the mass. Okay, so this is not in the effective theory. And in this theory, it should be obvious that there is a soft photon theorem, okay, because this is kind of derivatively coupled. Everything is like a function of the field strength. So it's kind of obvious and stupid, but let's still go through the motions and see that we can derive it using current algebra, and then we'll try to do better. Okay, so let's derive this photon Adler zero in just a theory of nonlinear electrodynamics. So just same argument as for the pion. Okay, we consider the current overlapping with a multi-particle state. There's going to be a one photon pole and some kind of smooth remainder. Okay, the water energy conservation of this current is going to tell me that I have here the photon amplitude, and here whatever is the remainder, but this is suppressed by Q. And then by taking Q going to 0 for the amplitude, then this power of Q will kill the right-hand side, so we get an Adler zero. Okay. So this is the same argument, and this shows that any scattering amplitude of photons in this theory will without any massless, without any charged particles, has to vanish. Okay. However, these higher form symmetries are abelian, so there's no interesting double soft theorem. So you might say that this is a bit boring. Okay, so let's see if we can do better and really derive the usual Weinberg soft theorem, or the low Burnett and Kroll. Okay, so if we're interested in the scattering of matter by soft photons, even though we want to keep the charged matter around, we are still taking the limit where the momentum of the photon is much smaller than the mass of the charged particle. Okay. Okay, so in this limit, the amplitude kind of at leading power should look something like a correlation function of Wilson lines. Okay, I will make this more precise in a second. So you will have some hard operator that encodes the scattering between the hard particles, and then the photon will just see a bunch of Wilson lines along paths which have to do with the kind of forward velocity of each one of these objects. Okay, so let's try to derive now a soft photon theorem in this setting. Okay, so now I have these Wilson lines with the charge of each one of the particles and some hard operator, but this is local, so this doesn't know about the one from current. Okay, so on the one hand, this will create a one particle pole, just like before. So now we'll have like the one photon state and the correlation function of these lines plus some remainder. On the other hand, I can use the word identity to relate this to this funny contact term delta function that I wrote before. Okay, so this is just using the word identity for the one from symmetry that I introduced here. Okay, so now let's take the Fourier transform of this. Well, as it turns out, the Fourier transform of this contact term is precisely the Weinberg soft factor. Okay, it's a simple calculation because this is just like a one parameter integral along this forward velocity, and this just brings this factor here, and then beta over red we can multiply by the mass, and we recover just the soft factor. Okay, so combining these two, the left hand side and right hand side, we get the Weinberg soft theorem. Okay, why is this justified? Where did this one from symmetry come from? Where did the Wilson lines come from? So let me make it a bit more precise. Okay, so for this, the useful formalism is this idea of heavy particle EFTs, right? So the idea is that we have some field, so this might be any field, and we can split it into positive and negative frequency modes. Okay, and then we can integrate out the negative frequency modes. Okay, so for instance, this is what we do when we go from relativistic quantum field theory to non-relativistic quantum field theory. Okay, so the idea is that you have the mass shell, which has the particle and the antiparticle, which are these two curves here. And then we want an effective theory that only describes particles which are kicked by a small momentum. Okay, so just modes which are around the particle mass shell, but not around the antiparticle mass shell. And then we integrate out the antiparticles. So this is a situation here, because the momentum, if we have a particle here or antiparticle here, the momentum of a soft photon won't ever be enough to kind of kick this particle off the mass shell and kind of perproduce. Okay, so since this is a theory where we integrate out the antiparticles, then there is no screening of Wilson lines. Wilson lines cannot end. They can only end in one direction, but not in the other, or you cannot perproduce and polarize a vacuum to screen their charge at long distances. Okay, and one can see this explicitly. So we can even like take now these positive frequency modes, do a field redefinition where we attach a Wilson line to each one of them. First of all, this claims the form of the amplitude manifest. So the fact that the amplitude will be related to a correlation function of Wilson lines. And also it makes the effective action a function of the field strength, which then has a shift symmetry. Okay, so this manifests the shift symmetry in the effective action. So indeed, the action will be invariant under the shift symmetry. So there's an emergent one from symmetry in this theory where we integrated at the antiparticles. Okay, so this is an exact emergent symmetry in this heavy particle limit, which is the limit that the soft photons see. Okay, so this kind of unifies the understanding of soft photons and soft pion theorems using these one-form symmetries. Okay, but okay, so do we learn something else new? Okay, so this is not, I haven't derived any new soft theorem. I've just kind of interpreted the old soft photon theorem with a new perspective and brought it closer to our understanding of soft pions. Okay. Now, is there some kind of symmetry that makes these talk to each other? Okay, so the answer is yes. There's something called a two-group. So I will now explain how we get some sort of soft theorem that knows about this two-group structure. Okay, so what is the formal description of this two-group? Let me just go over this very quickly because it's not so important. Right? The idea is that we have a zero form G and a one form gamma symmetries, and that can be intertwined into a two group. Okay, so what is the additional data for the two group? One is that if we have a line, a charge operator, a charge for the one form symmetry, if it intersects, so this is a codimension 2, so here I just wrote it as a line. If it intersects with an element of G, it might transform. So the charges the one-form symmetry might live in some representation of the zero-form symmetry. And then when you intersect three charges of the zero-form symmetry, you have some lower codimension line that could be precisely an element of this one form. Okay, so this is labeled by some group cohomology class. So, but roughly, this is a non-trivial extension of the zero form by the one form symmetry. In the same way that you can build a non-abelian group by an extension of a abelian group by another abelian group, and this is classified by some H2 class, some extension class. This is an analog, but for these higher form symmetries. So just think of it as some non-trivial extension of the zero form by the one form. Okay. What about current algebra? Here's even easier. Okay. So for a continuous two group, we just have an extra term in the word identity. So we have the original non-abelian term in the word identity of two zero form currents. So these are ordinary currents with the usual structure constants. But now there's an extra term with a total derivative here. So with a derivative of the delta function and the one form current. And there's some quantized structure constant here that you can roughly think of it as the structure constants of two pions and one photon. Okay, something that mixes pions and photons. If this was in kind of a broken, so if this corresponds to the broken generators of the zero form and these of the broken generator of the one form, then this structure is very suggestive. Okay, so we'll denote this as this, and this suggests that there should be a self-theorem that mixes up photons and pions in some way. And because it's in this word identity, it's probably a double self-theorem. So let's unpack this. Okay, so let me say something else about this two group. So this might seem something very exotic, but it's not that exotic. It's basically the fourth kind of triangle diagram when you have something like anomalies, right? So we know that if we have some gauge current, and then we look at this triangle diagram, and it's non-vanishing, then this is just a gauge anomaly, so this is an inconsistency of the theory. Okay. If we have a global symmetry, we can also look at the triangle with the global currents at the corners, and this gives us an 't Hooft anomaly, meaning that if I turn on background fields, then I will see some non-zero right-hand side. Another way of saying it is that there is a contact term in the three-point function of the currents. But if I don't turn on these background fields, if I look at separated points, the symmetry is just conserved. Okay. Another example is the usual Adler-Bell-Jaquif anomaly, where you have one global and two gauge. Okay, so this is the case of the chiral symmetry in QCD, where we have like the global chiral current. It's broken by either E&M or gluons. Okay, so this is the symmetry really being broken. And the two group is the other option, because basically this contact term in the word identity that I showed you in the previous slide, it corresponds to a triangle diagram with two global currents and one gauge current. So this thing, if I take a further derivative with respect to the background field, then I have one power of f, which precisely corresponds to this. Okay, so it's just the missing triangle diagram in 4 dimensions, if you wish. Okay, so it's not something that exotic. It's very familiar to things that we already know about. Okay, so let me just make one historical aside, which I think it's nice. So actually, this structure of a two group was first characterized in the thesis of a Vietnamese mathematician called Hoang Xuan Sinh, and she was actually a student by correspondence of Grothendieck while he was at IHS, where I am now, and so actually he went to lecture to Vietnam during the war in the north while the war was raging on, and so there's some very interesting story about there's some like spies involved, and she had to like look after him, and so if you're interested, you can ask me next time we meet. But yeah, so this is something that goes back to the kind of 60s and eventually found its way into physics. Okay, so of course this was in a very abstract mathematical setting where this was, so it's a bit hard to recognize. But I encourage you to look at this story. Okay, so what is an example of a theory with a two group? Again, is not something very exotic. Okay, so take quantum chromodynamics with massless quarks and just gauge the vector symmetry, just baryon number, just gauge baryon number. There is precisely such diagram because there is a mixed anomaly between baryon number and the chiral symmetry of QCD. So if you gauge baryon number, you will get this sort of triangle diagram. So this is the theory. It's just the chiral Lagrangian with a new photon for baryon number, and this is just the coupling to the current, which is this anomalous baryon current that we can write in terms of the pions. Okay? And as I said, it just comes from the mixed U1 axial 't Hooft anomaly which yields this two group between the chiral symmetry and this magnetic one form symmetry for the new photon after gauging. Okay, so this is just the dual field strength as before. And indeed there is a soft theorem. I will spare you the details, but it's basically again a current algebra proof, just like the one that I explained before. Okay, so so let me explain the pieces. So again, here we have an amplitude where I have n pions and n photons in a theory that has the symmetry breaking pattern. Okay, and here I have n plus 2 pions, sorry. So I'm going to take 2 pions soft. So I'm going to take the momentum of these 2 pions soft. Okay, and there's going to be 3 terms in the soft theorem. The first 2 are the ones that I already showed you before. So the leading soft theorem is unmodified. The subleading soft theorem is this one that I showed you here. Okay, so there's this leading and subleading soft factors that depend. So these just give amplitudes which have 2 fewer pions. But there's some more interesting term that arises, which is this. So at the subleading level, there's a modification of the soft theorem that looks like this. So there's this epsilon tensor that appears, and then there's a structure constant if the two group current algebra. Okay, so there's this term here in the current algebra. I wrote it schematically, but appears at the subleading level. And actually it appears in 2 different ways. So I have an amplitude. So this thing, I started with n plus 2 pions, and then it gives me an amplitude with, even though I'm taking 2 soft pions, it gives me an amplitude with only 1 fewer soft pion and 1 fewer photon. Okay, so this is not an amplitude now with n pions and n photons, but n plus 1 pions. So you're turning a photon into a pion by taking 2 pions soft. So this is the action of this 2 group that is mixing pions and photons, and vice versa. Okay, so if you take 2 soft pions, there's a term where now you remove an extra soft pion. So compared to the original amplitude, this amplitude has 3 fewer pions, but it has 1 extra photon. Okay, so this realizes this idea that there is some sort of soft theorem that mixes the 2 types of Goldstones, and that it's associated to this kind of spontaneously broken 2-group symmetry. And indeed, the derivation is just derivation with current algebra, starting from this, looking at 2-point function of these currents, and turning the crank, and it's a very common derivation. Okay, so yeah, so these are the comments. So as I said, the proof follows just by considering this 2-point function in the presence of some on-shell state and using the new term in the 2-group wide identity. But other than that, it's just like the double soft pion proof. The fact that this contact term has an extra derivative here corresponds to the fact that the soft theorem appears at the subleading order. So this leading soft double pion theorem was not modified, but the subleading soft was modified precisely because there is 1 derivative in this contact term. Okay. And because this proof follows from current algebra, this is not corrected by loops or anything else. This is not a diagrammatic proof, which is the advantage of these current algebra proofs. Okay, this is not, I take a bunch of diagrams in some particular theory, I expand them, I get a soft theorem, which might or might not be corrected. This follows from the current algebra, so it's a non-perturbative statement insofar your theory exists non-perturbatively and has this symmetry, which is a different question. Actually, there's some kind of subtle questions of whether you can have UV complete theories that have these higher symmetries, but let me not delve into that. Okay, and we check this explicitly in all 3 amplitudes in this theory up to 6 points. Okay, so we took this theory of like kind of the nonlinear sigma model coupled to some with this anomalous baryon current to some photons, and we computed all possible amplitudes up to 6 points with any number of photons and pions. Okay, so now these amplitudes can have also odd numbers of photons and pions because of this coupling here. And we check that in all of those amplitudes, the soft theorem is satisfied. Okay, so let me give you an example. So here we have the 6-point amplitude where we have 4 pions and 2 photons. So you don't need to know what this kappa is, but it just takes this form. So these are the momenta of the pions or the photons. These are the polarizations. Okay, these are usual Mandelstam invariants. This is P1 plus P2 squared, P1 plus P5 squared. And now we just take P1 and P2 to 0. Okay, so we predict from the soft factor acting on the lower point amplitude, we will predict the following structure. So this relates to an amplitude that has 3 pions and 1 photon. So naively, we would have gotten 2 and 2, but at subleading level, we have this new term, and here we also have 3 and 1. And indeed, you can check that if I'm taking 1 and 2 soft, then just this term goes away, this term goes away, and then I get precisely this structure. Okay, so this precisely matches the prediction from the soft theorem. Okay, so I think I went very fast. But okay, let me summarize and just make some comments. So hopefully I convince you that there is this new angle on soft theorems from this one-form symmetry, soft photon theorems. Okay, so we can prove the soft photon theorem using current algebra arguments, just like the ones that prove things like the Adler zero. I didn't need to invoke asymptotic symmetries, large gauge transformations, anything like that to prove this soft theorem. It was just some statement about current algebra and ordinary, well, higher symmetries, but ordinary in the sense that ordinary symmetries with a current in quantum field theory. Okay, so let me comment that it seems to also work for gluons and gravitons. I didn't explain this, but there's the idea that soft gluons, say for instance you have an infrared free gauge theory, you can think of the soft gluons as the emergent, as the Gaussian bosons from a bunch of emergent one-form symmetries at the free point. Okay, and similarly for gravitons, and then one can derive the soft gluon and soft graviton theorem from a similar perspective. Okay, for gluons, I mean, this is only valid perturbatively, but that makes sense because soft gluon amplitudes only make sense perturbatively. So this is the idea that this symmetry is only emergent at weak coupling. Now, is there a connection to the story at Scry? Well, I hope there is. And one way that you might think about this is that I told you that in this proof of the soft photon theorem, I needed to use this correlation function of Wilson lines that stretch all the way to infinity, right? So presumably the fact that this transform under the one-form symmetry is related to the fact that if I do a large gauge transformation, the point that pierces the celestial sphere, or just I plus, this will transform. Okay, so I hope that there's a way, this might provide a more direct way to connect these higher form symmetries to things like asymptotic symmetries. But okay, one still has to do it. Oops, sorry. And is there a connection to this geometric perspective that I didn't talk about, but this idea that kind of soft theorems just move you in the moduli space of vacua? For pions, we know for sure this is the case. The zero is because if you have a symmetric coset, by taking a soft pion theorem, this is like constant shift in the field. So you're just moving around the manifold, which is the set of vacua, which is identical at every point. That's why you don't see any change. It would be nice to understand if something like this can be also thought of, developed for photons, the idea that somehow the vacua are labeled by some large gauge transformation, and then maybe also connect to the story of Scry. I think one kind of side output of our work is that maybe these emergent higher symmetries are kind of ubiquitous in Lorentzian effective theories. I gave an example of this heavy particle EFT where there was an emergent one-form symmetry, but maybe in things like heavy quark effective theory or soft collinear effective theory, which are theories that naturally have Wilson lines that play a very important role in things like factorization theorems, things like that. Maybe these higher symmetries can clarify some the structure of these EFTs, and maybe they're related directly to factorization theorems. And I also presented a new soft theorem for this two-group structure that intertwined soft pions and soft photons. And I think this is just the tip of the iceberg. I think there's likely more soft theorems to discover if one uses these new symmetries as a guidance. One might wonder if things like these non-invertible symmetries also have implications for soft theorems. So I hope to explore all of this in the future. And even though I still have about 15 minutes, I think I will end here. And thanks a lot.
Thanks a lot, Julio, for this very interesting talk. Thank you. So, are there any questions?